today's warm-up, when you see a factorial, what test do you, is like your default? Ratio test, right? So you use the ratio test on this one. Hey, I spotted the n factorial. I use the ratio test to get da-da-da, right? Now, here's my guess. I'll bet most of you guys made it to here, right? And then you weren't quite sure if this was less than or greater than 1 or what to do from there, right? Okay, so I'm going to give you a mild hint. I would be very aware and alert for this guy right there. Because when you take the limit of that right there, it's E. We've learned this before, but it's been a while since we've talked about it. It might come up again. Right?
Come up again or quiz come up again?
I don't know what's on your test or your quiz. I'm just saying it might come up again. Right? Okay. Yes, Will?
Without memorizing just that, is there any way to figure out?
There is. If you had to figure this out mathematically, what you'd have to do is set your limit equal to y, and then take the log of both sides, put the exponent out front, and then apply L'Hopital.
Good stuff.
Yeah, it is good stuff, right? Yeah, it's what you did last chapter. Yeah.
That's what I did.
Like that.
So there you go. If you can recognize that the limit as n approaches infinity of n plus 1 over n to the n, which, by the way, is the same thing as 1 plus 1 over n to the n, right? This or this, those are equivalent. If you recognize that the limit of that is e, that might come in handy.
Wait, that was on the quiz, wasn't it?
I don't know what's on your quiz.
No, not like on the tan thing you said.
I don't know.
It was one of them, I'm pretty sure. It was like X
Yes.
plus 1.
I did the root test, is it like, okay to do that, or is that one not?
Of course, yeah. Let's see, so you got 4n over 9 times the square root of n factorial, and you are taking the limit as n approaches infinity, so you'd end up with a limit of, did you get a limit
I got
of
like
0?
4n over n, or 4n over 9.
4n over 9 times the square root of n factorial, right?
Yeah, but then there's like 1 to the n, right? So
Let's see.
1 to the n, or not 1 to the n,
Or the nth root of n factorial.
Yeah.
Yeah, so how did you do that from there?
Well, n factorial, if you did it to the 1 over n power, then that just makes the 1 over n 0, and make the n factorial
Go to 1?
Is that like mathematically sound?
Yeah, I think so. Let's see, if we do the limit as n approaches infinity of the nth root of this. Do you guys hear what she's saying?
Yeah, yeah.
Okay, so limit n approaches infinity of, so this is just 4n over, this is just 9, and then this is the nth root of n factorial, and so,
You should write it as 1 over.
yeah, that's what I'm about to do. So this is the same as n to n factorial to the 1 over n, right? And as n approaches infinity, this is going to go to 0, this is going to go to 1, and you end up with a limit of infinity.
Okay, so I just wonder if n factorial.
The only thing I worry about is, does n factorial to the 1 over n really approach
I know,
1?
Right.
I'm not sure I have a big comfort
why
level
wouldn't-
with that.
Oh.
Because you have infinity to the 0. And infinity to the 0 can play games. And
Is that an indeterminate?
I don't know.
I
You
think
have
it
to, well, it's certainly indeterminate, but I don't know then if when you manipulate what answer you get. You probably still get one, but I don't know. Yeah. So, yep. Okay. Okay, good. Any questions? Do y'all understand now what I was saying? Hey, it might be good to know. All right, good. Moving on. So there's some homework problems in here. Feel free to peruse them. All right, so today we're doing 910A. Oh, guys, we're on the first day of the last section of the chapter. Okay? And I have good news. The last section of the chapter is not the most difficult section of the chapter. So, I personally found 99 to be the most difficult when I was planning.
I would agree.
Okay.
You don't know what's
Could
yet
be
to come though.
Could be like,
I think you'll still agree.
you have to take the integral of the polar coordinates of the Maclaurin series.
Okay.
That's what this unit's gonna
Yep.
be.
Wait, do we
Okay.
have to do polar coordinates in this class?
Yes, next chapter.
Why would you say that? Never had to do this?
You don't know how to do them?
It's all right, the rule-
Isn't it like r theta or something?
Yeah, r sine theta, r cosine theta.
Sine
It's just, yeah,
That's X and Y.
yeah,
And you always
Oh,
do
yeah.
X squared.
Well,
plus
yeah, I
Y
thought
squared
y was
equals
theta.
R squared.
yeah. See, it's just a radius and an angle, it's all right, it's all right.
I'm behind.
Okay, so anyway, a Taylor polynomial, this is a review. What we're doing in this section is we are bridging section 9.7 with sections 9.8 and 9.9 to create 9.10. But 9.7, if you remember, were Taylor polynomials, Taylor and Maclaurin polynomials, right? The main thing that we're taking from 9.8 and 9.9 is just we're going to take those Taylor polynomials and learn how to write them as series, which means with sigma notation. All right? So, we have this lovely Taylor polynomial here. It's just the generic formula for a Taylor polynomial. I want you to take a second and see if you can write a generic formula for a Taylor series. All right, just take that polynomial, see if you can figure out a generic Taylor series formula.
Why is 0 factorial 1?
It was defined that way. I asked that exact same question. I remember asking that exact same question to my math professor when I was in grad school,
What was the one of that?
and his answer was, that's how it's defined.
That's stupid.
Live with it, yeah. So anyway, that's just how it's defined.
Well, in 30 years they looked at it and they're like, oh, wait a second, 0 factorial is actually infinity.
Well, what's your question?
What was the one that was like,
Darn.
You don't remember.
You should, have you ever done any further research into that?
No, I haven't.
Because there was like, there was one thing that we was like, one was just basically.
Are you allowed to write it with like 3?
Can you, yeah, that's what I'm asking.
You should look at.
Like F to the N
F to the
of,
N.
yeah.
When this
Like you
is
write a
done,
prime
I
as an
will-
N.
Because
Okay.
that would be really.
Like the prime,
I
yeah.
will also tell you the mathematical news of the day at the end of the lesson, because there's actual mathematical news today.
You're gonna make us what happened?
Yes.
Oh, you might
Okay.
write it
I
as
am gonna
N
make you wait
minus
the full
1
hour to
times
find out
X
that-
minus.
Oh, yeah, I was trying to
Is
one
it
up
about
the
the
villain
professor
and
or something?
Did they come up with this symbol?
Yes, yes.
They come up with
But
this
we've
I was
already,
like, good.
the
Well, you took
difference
the-
between what
Oh,
you know
yeah.
is
But-
that my students from last semester, we had already talked about that professor and the math thing that he solved. So the only new news is the money he got. Which is kind of interesting. Yeah, okay, yes.
So somebody explained it on Google about why 0 factorial is 1.
Oh,
They
okay.
said- So they said that that like factorials, what they actually do is kind of like 3 factorial would be 3 times 2 times 1 times 0 factorial. So like it keeps on going where 0 factorial is the end of that. Kind of like it'll be 3 factorial is 3 times 2 factorial. It keeps on going.
Sure. But
Whereas
what
0
about, why does it have to go to 0? Why doesn't it just go to 1?
It's just using it as like an example because it talks about it's a
nothing.
odd
That
like
proves
30
nothing,
species or
yeah.
something.
That
So
just
it's-
like-
well no, its point is it's just saying there's an implied 0 factorial in a way. Kind of like because it keeps on going like with n factorial,
Yeah.
that's n minus 1, n minus 2, n minus 3, n minus 4
But then
factorial.
It justifies
in
No,
that
no.
process, you could go to negative numbers.
Yeah, exactly. But its point is just it's saying like it's all the positive integers and 0 can be considered a positive integer in a way.
No, it's not.
This is theoretical, Mr. I will say that if in factorial, this right. Look at this. Wait, you're on camera. You're on camera. You better remember that was the one who found this.
Dylan, you're famous now.
People are gonna hate you if you're trying to learn.
Dylan, you're crazy.
They're gonna be like, these people.
I did a bad number.
Greatest day of my life. Greatest day of my life.
Hey, what are we
Yeah.
gonna do right now?
I see what they're
Yeah.
I don't know if that really explains it, but I guess that's a nice
It's a way of
way of
explaining it.
What?
explaining it.
Date
Why
make
does
it come back?
Alright, well, let's not get into it. So, here we go. So if you write a Taylor polynomial using sigma notation,
Cool.
it's really just the sum of, how do you write that derivative? That's the hardest part, right? You just write the nth derivative evaluated at c, right? It's the nth derivative evaluated at c times x minus c to the n over n factorial. Everyone good? Okay, even with the diversion? Alright, good. Let's move on. Alright, so here's what I want you to do. I want you to take a few minutes. I want you to write a Taylor polynomial for e to the 3x centered at 0, and then I want you to convert the polynomial to sigma notation. But I want you to write the polynomial first, then write the sigma notation. Alright? So you'll need to write those first few derivatives.
Just like 3.
Yeah, I think I just went to f triple prime. I think that's enough to see the pattern.
Do we even have to like see the pattern?
Yeah. Because you can't just write every sigma as f sub n of c. You have to actually put what's there as a series, like as a formula. So you need to know what the pattern is for the nth derivative.
Okay, okay, gotcha.
He can be the publisher.
Or just be. Well, if I was gonna do 1, then it's like.
Okay.
Wait, it's gonna be 1.
Yeah, plug in 0.
Yes. You're gonna go 1.
Wait, but then if you take the derivative.
So it's 3, 9, 3, 9, 27,
You want to
81.
start with the
Just
polynomial, not the
yeah.
sigma.
3 to
So I would start by finding those first few derivatives of the 3x,
So you get 3
and then plug in zeros. See what happens.
oh,
Good.
times
Okay.
x to the n. Over n factorial. So 3n, or 3x to the n factorial.
What was the formula for this one?
It's FC.
Oh, this is, yes. Oh.
She threw her voice.
Times x minus c.
C is 0, right?
Don't hurt yourself.
Oh, okay. Start with the polynomial first. Oh, you have to do that. Okay. Sorry. Okay. I think everyone here has got the first few derivatives.
Well,
Remember, you want the derivative evaluated at c, right? So you gotta plug the zeros in.
Should we do it like that?
Remember when we write Taylor polynomials? The first thing that you've gotta do is find those first few derivatives and plug in the c's, right? So, yeah.
That's why.
Once you've got that, now you can write your polynomial.
That's why 0 factorial. It says so.
Wait, how do you? So I know we wrote like f to the whatever.
That's the nth derivative at
Yeah.
c, yes.
So how do you do that when you have the actual function? Like,
That's you
Well,
have
use
to
the
start with the polynomial, that's what I'm saying. You can't start with the sigma. You've got to start with the polynomial. Because you'll never see the pattern unless you actually create the polynomial first.
will there always like be a pattern?
Yeah, but it's not always easy.
Of course it's not.
I don't even know what the difference is. It's like 3
Good work,
Just
Trey.
write out the polynomial.
Stop trying to skip steps, Trey.
No, I wrote out the polynomial.
Did you get that for your polynomial?
Yeah.
Good.
See.
So to convert from a polynomial to the sigma notation, I just kind of break it apart. The easiest part for me is just, let's start with the x's, right? So how am I going to write the x in my sigma? X to the n, right? Okay, good. One of the things that can make it easier for you is to not actually multiply out your factorials. So I did in my examples, but I'm kinda thinking it would probably be easier for you guys to see if I kept that as, like, wrote 1 factorial, 2
Oh,
0 factorial, 1 factorial, 2 factorial, 3 factorial. The reason that sometimes I multiply the factorials out is because sometimes they cancel with the derivative, right? And you end up with a nicer series. But oftentimes they don't. So sometimes it's easier, just keep them in factorial form so that you can just write n factorial. Everything else you just Alright, so that's that. So we've taken care of the x's, we've taken care of the bottom. What about the coefficients here? 1, 3, 9, 27, 81.
They're
3 to the end.
Yeah, they're just 3 to the n, right? So our final series, stop putting dots on everything. Our final series is 3 to the n, x to the n over n factorial. And then I just wrote it as 3x to the n, but you could either way is fine. Does that make sense? So the whole point of going from a Taylor polynomial to a Taylor series, you've got to write the polynomial first. Because you can't just put f to the n of c here. You have to actually have a function, a thing for it, right? A representation of it. So if you write out the polynomial, then you can see the pattern and put it into your series. And that's how it's going to be presented on your test. It's going to say, write the Taylor polynomial for blah, 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 right? And you write out the Taylor polynomial, however many terms it says. And then the next thing, of course, will say, all right, now write it as a series. Right? Write the series.
Then are we gonna have to find convergence or divergence problem?
And then you might have to do that, and maybe you have to find out how many terms to get it within a certain error if you were to sum them, and yeah, see how you can take one problem and just keep going with it and cover all the sections, right? Yeah, so, anyway, okay, so try another one. So find the Taylor series for f of x equals sine x, centered at c equals pi fourths. Pi fourths.
No, it's fun.
There's a note there that I gave you because I wanted to save you the headache of having to figure out what exponent to put on your -1 term, but you'll see once you work this out why it's a headache.
Sine.
So what's the first thing you have to do?
Right out the polynomial.
Find out those first few derivatives of sine, right?
3, right?
You should just-
3 or 4. I would probably do maybe
Because for sine.
4.
Oh, yeah.
No, because.
You do 3, I don't care. Just as long as you recognize the pattern. I've never sat on the ball before.
Isn't it fun?
Quite comfortable.
It's kind of lopsided.
We
Yeah.
could say that
Like,
I
if
am.
you like roll it across the ground, it's really lopsided.
That's because it's like,
But it's comfortable. So.
You could say I'm on the ball today.
Or
We should get that on camera.
Not say that.
I think we just
What are you trying to say about
that.
Miss Price's teaching today?
JJ, do you have something to say?
Calm down.
Alright, that's enough, that's enough.
No, you gotta let the roast happen.
Ooh, can I give a little shout out to Glenn Berman watching these videos at home?
Skipping, he came to first and second, aren't you know that, Chris?
Yeah.
Came to first and second.
He said that he just wanted to skip calc to watch March Madness. That's what he told me in the second hour.
Okay.
And then yesterday he shows up to bingo.
No, I'm just kidding. I just wanted to hear about
Heard Tommy.
I
Oh,
was
yeah.
just doing
No,
something.
No, he emailed me, he's on top of it.
No, I know, yeah. I just wanted to hear that in the video.
So let me get this straight. So if someone emails you why they're not gonna be in class, you don't have to show up.
Yes.
Well,
No.
but
You need to have a
Yeah,
balance.
that's what
If
Glenn
you-
said.
I gave you a Miss Price.
I mean,
don't feel like comfortable
if
about
you
it.
email me and what you're telling me is truthful, right?
Well, and I mean,
If you email lies, it's just the same as saying.
I think Glenn Berman's email.
But you don't take it
Right,
serious.
Right,
so
and
it's
it's not like I
like-
can't excuse you, I still mark you absent. right? I'm not your attendance
So
clerk.
parents.
That's between you and
Although,
the attendance office.
To be honest, the attendance office, like, you can call yourself.
I know people who
All
have
right,
done
that's
it.
enough, we don't need all this on film. So, here we go.
Not
So
saying.
derivatives,
A friend.
there. Okay, so at pi4, sine and cosine are both root 2 over 2, right? So you end up with root 2 over 2 for all of them, but the signs of the functions go positive, positive, negative, negative. If we kept going, they'd go positive, positive, negative, negative, right? So you get a little problem when you write it out as a polynomial. It's not a problem here, but to convert to a series, making signs go positive, positive, negative, negative is tricky, right? So one of the things that I did, I multiplied out my denominators, but nothing cancels, so it's probably easier if you keep it separated and you have 2 times 0 factorial, 2 times 1 factorial, 2 times 2 factorial, 2 times 3 factorial, and so forth, right? To see the pattern. All right, so tell me something that you know is in every term and will be in your series.
N factorial.
There's an n factorial on the bottom, right?
2 times 2 over 2.
You know there's a root 2 over 2 in every single term, right? So
Yeah,
now
see
we've
it.
got root 2 over 2 of root 2 over 2 n factorial, right?
X minus pi 4 squared.
X minus pi 4 to the n, right? So we've got everything counted for except the negative. So the way that you make these signs alternate is use an exponent of n times n minus 1 over 2.
We're gonna need to know that.
Okay?
Is that just a memorized thing or?
No, it's okay. But you might need it for your homework tonight.
Oh, so it's not on the test.
So it's not what?
We still boycott the whole.
I don't know what's on the test.
Did you say you took the test?
I don't know what's on the test.
Yes, you do.
You should do, you took the test.
I have no idea what's on your test.
I think she's
You took
lying.
our test, how could you forget?
Is this test on chapter 7?
Blink twice because you have a teacher.
So,
Still on camera.
so anyway, here's the thing, believe it or not, this is kind of a fun little function, because if you plug numbers in, and you can mentally do this and test to see if it's true, you're gonna end up with even, even, odd, odd, even, odd, odd, and you get that repeating pattern. So you end up with positive, positive, negative, negative, and it works. So there you go. All right. But the most important part of this is, can you take the rest of it and write it as a series?
Is this the farthest we're gonna go with these problems, or are we gonna go?
Can we not go further?
Let's go a little further. Okay. No, they don't get much harder, they're just, you just change. So, the last type of series that we are going to learn in this entire unit is the binomial series. You have done binomial expansion in the past,
Oh, that's fun stuff.
right? It is fun stuff. Yeah, and you get to use which wonderful mathematician's triangle?
Pascal.
You get to use Pascal, right? Oh, who doesn't love Pascal?
Me.
So,
Oh, Pascal's
I hate
he
Pascal.
does the
Oh, yeah,
coefficients
He
of
just drew
binomial
one,
expansion,
broke
right?
one, and then it's like, let's make
All right.
it here.
So, anyway, but we are not using that in what we're doing today. So, which is too bad. So here we go. Everyone's talking about the triangle. You could spend days just looking into all the series that are within Pascal's triangle. So there's tons.
Does
Of
We
really
had like a
Triangle have
challenge
any
in my
limits?
freshman year in Algebra 2 where we were like, hey, like, who can find the most complicated series? And then I found one and my teacher was like, that's not a series. I'm like, yes it is, and I proved it. She's like, I don't count that, but she didn't like me very much. So, she also didn't give me my bonus points on like some things. It really made me mad. She accused me of cheating like 10 times.
Oh, I'm
Well,
sorry.
She also accused my brother of cheating.
Yeah, you told us this already.
He didn't pay attention to her class. He thought he was
Basically,
an
if you were related
You were a Sal?
associated with him.
No.
Okay, so here we go.
I sat there and did nothing all out.
So a binomial series is the expansion of 1 plus x to the k. And what we're going to do here is find the Maclaurin series, just the polynomial, not the sigma notation, just the polynomial for f of x equals 1 plus x to the k. So what I want you to do for the next minute is find the first 3 or 4 derivatives of 1 plus x to the k. Differentiate with respect to x. K is just a constant, alright? So differentiate 1 plus x to the k and evaluate those derivatives when x is 0. Because it's a Maclaurin series. I'll even start it. There's the first one.
Wow.
That was great.
Isn't that good? Because 1 to any power is 1. We're going to go with 1 to the power is 1.
Yeah.
So once you've got your first few derivatives evaluated at x equals 0, see if you can go ahead and write out the polynomial.
We could be like 1, 2, 3,
This is good. Oh, okay.
Wait, if you have factorial.
Yeah, perfect. And now what you want to do is plug in a 0 for all your x's and see what you're left with.
Can this be, if you get a factorial over a factorial, can you combine them?
Yes.
Wait, no.
No, it depends.
Yeah, because then like if you subtract 1
Yeah,
from
yeah.
3 halves, they'll be different than subtracting 1 from
No,
3
it's
and
factorial.
2.
Well, you can't do it, no, you're right, 'cause you can't do a factorial of non-integers. They have to be integers by definition.
So this is minus 3k squared.
But so would this not work for any like 1 plus x to the 3 halves? Like if you had x equals 1 plus x to the 3 halves, would you not be able to do that because you use a factorial?
You don't have to write it in factorial.
But when you do the summation, when you write it as summation.
Yeah, it's k times k minus 2,
Write it as a
k minus 1, so it's like all the previous here.
So,
No, when you write the summation, you write it.
oh, that's why you don't write the summation.
Oh,
You just write it as a
I think
fact.
so.
but that's hard.
So there you go. How did you do with your derivatives? Did you see pattern? Okay. All right, good. You got it? What was that you? Good. All right, good. That's all we're gonna do with that. We have one more type. Yeah, it's really helpful.
What did
Wait, I
we
thought you
do?
said binomial was the only
What did we just do?
one you left.
We just kind of learned how to expand a binomial. You're going to do the same kind of thing with binomials tonight, maybe 1 plus x to the third, that kind of thing. So
Wait, tomorrow are you gonna like expand this or are you gonna
no,
do something different?
tomorrow's different.
Okay.
Tomorrow is.
Oh, actually we have one more. Sorry, one more of this type. Oh, that's right, I forgot about this. All right, so use the binomial series we just found to write the Maclaurin series for square root of 1 plus x cubed. Now, ignore the x cubed. Just think 1 plus x. So we have square root of 1 plus x. What's k?
1
1/2, right? It's just 1 plus x to the 1/2. So, woo, okay. So, yeah. All right, so there is our Taylor polynomial. We just came up with it on the last screen, right? So what I want you to do now, thinking that k is a half, don't worry about the x cubed, just think k is a half. I want you to plug the 1/2s in.
Into the case.
Mm-hmm.
That's fine.
Twice.
Wait, what is that? You just plug an x cubed into the x then after that?
Don't you, at the end, we'll do the x cubed.
That's fine.
All right, y'all plug in your halves. So let's see what we've got so far. Hey, that's fun.
No.
That sounds quite cool, that's horrible.
Okay, so we have 1 plus 1/2 x plus 1/2 times negative a half, right, with the x squared over 2 factorial. 1/2 times negative a half times negative 3 halves times x squared over 3 factorial. 1/2 times negative a half times negative 3 halves times negative 5 halves, right, times x to the 4th over 4 factorial. And you keep going. The next one you'd multiply with a negative 7 halves, right? Okay, good. So what we're going to do now is write this as a series.
Can you do a factorial to like a certain iteration? Like, can you?
That's the question. So I researched to see if there was a way to do a factorial version of 1 times 3 times 5 times 7 times ... right? And it ends up being 2n minus 3.
Oh, okay.
So, yes, there is a way to write this with factorials, but not with 1 factorial. It requires a quotient of factorials, and they're not easy factorials. And so because it is a tricky thing to do, we don't do it.
We just do that.
We just do this.
Because we don't.
I think that's what they do in our book too.
What
It
is?
is. So I did look it up, and yes, there is a way to do it. There is no way to do it with 1 factorial. You have to take like all the terms and then divide out a bunch of terms. So it has to be done with multiple factorials. So here instead, tell me easy things that we can put in our series. X to the n, right? Good. Tell me something else easy that we can put in.
Over factorial.
Over n factorial, right? Okay. So we've taken care of the x to the n's and the n factorials, right? So these guys, those are good. Those guys, those are all good, right? What about all these 2's on the bottom?
2.
It's just 2 to the n, right? So our denominator is done. It's just 2 to the n factorial. Okay, everyone okay with
Why
that?
is it 2? No, why is, oh, it's, never mind, I got it.
Yeah.
You're multiplying the 2.
The 2's, yeah, they are.
I was thinking, but the 2 doesn't change, it's just always 2.
Ah, but you add more 2's.
Yes, but
They're
there's
multiple,
more-
yeah,
there's multiple of
they
them.
increase.
How do you do
They multiply. Okay, the negatives. Do the negatives alternate?
No.
We have positive, positive,
Oh,
By
yeah.
negative 1 to
negative,
and
positive, negative, positive, negative. They alternate for all the terms except this pesky one at the beginning, right?
That's
Okay, so let's ignore that one and just think, hey, okay, we're all right. We can do a negative 1 to the, it wouldn't be to the n because this is n equals 2 and it's negative, so negative 1 to the n minus 1 or negative 1 to the n plus 1. All right, so we're good with our negatives. The only part that's tricky is this 1 times 3, 1 times 3 times 5, 1 times 3 times 5 times 7. And the way that you write that is like this. So that's the cutest way you've got, unless you want to do these quotients of factorials that are quite complicated. So here's what we've got. We have negative 1 to the n plus 1, that's our sign. We have 1 times 3 times 5 times ... times 2n minus 3. So what you do is you multiply every odd number until you, ending with whatever you get when you plug in your n value. Times x to the n over 2 to the n factorial. Alright, so why did I not include the first 2 terms in with my series?
Because you can't do the negative 1 thing.
Because that darn alternating sign messes it up, right? Yeah, so I think, I hadn't really thought about it, but I think this one could have gone in there.
Yeah.
Yeah. So I could have just left the 1 out, but that's not good.
So how come you didn't do the negative 1 to the n times n minus 1 all over 2? Because it switches like even, I mean.
No, it doesn't go every other, it literally goes, every term it changes.
Oh, okay.
Yeah, that one was when it was positive, positive, negative,
Yeah.
negative. This one literally goes positive,
Oh,
negative, positive.
okay.
So this one's a simple one. Alright, so we've got that answer, blah, 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 blah. Okay, now we've got to take care of the x cubed. So we've got our series, but this series is actually just for the square root of 1 plus x. We want the series for the square root of 1 plus x cubed.
Just plug it in.
Just plug in an x cubed for x, right? That is the beauty of series. So, take your, this is piece of n of x. If we want piece of n of x cubed, I want you to just replace your x's with x cubes.
Wait, but then when you get,
And then that's an x cubed.
so you can't really
Okay.
write it as a factorial.
No, you can't.
But then when, can't you just do -2 plus 1 as well?
I'm sorry, what did you say?
Sorry, never mind, I'm saying.
Alright, so we have, so this becomes x to the 3n, this becomes an x cubed. Is that, y'all okay with that? Changing the input is easy, right? When you have to change the input on a series, you just change the input on the series. Okay. These series are in your book. I made you all take a picture of them yesterday, right? Is there anyone that hasn't taken a picture of them yet? Okay, you might want to take a picture. Oh, you can just pull it on the smart board. It's on yesterday's and today's, because you use them even more tonight. So, does anyone need to take a picture? You're all good? Okay. All right, good. So you're going to use these again tonight. Here's how you're going to use them. You can use the series we know, to create new series simply by changing the argument. For example, find the Maclaurin series for the function g of x equals e to the -3x. So let's start by knowing the Maclaurin series for e to the x. So there's the Maclaurin series for e to the x. So how would you change this to a series for e to the -3x? Yeah, just change your x to a -3x. Everyone take a second to do that. Okay, so we're going to do e to the -3x. We just changed the x to a -3x, and you end up with -3x to the n over n factorial. Whoa! Is that okay? Not too tough, right? All right, ready to try one? Okay, you're going to find the Maclaurin series for g of x equals 2 times the sine of x cubed. That's x cubed, not sine x quantity cubed, but just the sine of x cubed. So, I'm going to tell you right now, this is from our little list of series, that the series for sine x is this. I want you to see if you can then use this to find the series for 2 sine x cubed. Go.
Do we need to show any math, or can we just put, do we need to show any math, or can we just plug stuff in?
You can use magic on this.
Please don't make me do this to Paula, you can do it, I'll pick it up after this.
Yeah, there's.
Oh, I told you, I'm so proud of myself.
The same thing the one that we had before was with a punch. These people saw mine strings, and so it was funky. This one is centered at 0 and it ends up being normal.
For this one, you multiply the whole sum for like
You can put the 2 in front of the sigma.
Okay.
But at like the.
And then
His
just plug in
sister
x.
His sister plays.
12.2.
His sister
Yeah, no, the entire game. No, it wasn't like a
It feels
huge deal.
wrong.
It does feel wrong, I know.
Did you guys
You got me nervous.
No, yeah.
You got me.
Okay,
They're gonna
so,
come back.
if you want 2 times the sine of x cubed, that's just 2 times the sine of x cubed. So you can take the sine of x cubed and then just times it by 2, right? You can have the 2 in front of the sigma or after the sigma, it doesn't matter. I put it on the inside, but if you put it on the outside, that's absolutely fine, right? So, blah, 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 blah.
You need to get the,
I know.
our series.
Yeah, I
Dude, finish me.
That's
Such a long week. So put the 2, replace the x with an x cubed. Right, multiply by 2, replace the x with an x cubed. I just went and distributed the x bar. Right? Good? Yes, you could absolutely take the 2. I really meant to do that, right? Okay.
Between that essay was.
So you can take the 2 and put it in front, and that would be fine as well. Alright. So, now, quick question.
What happened with
That's not the question. So,
What's a Taylor series?
okay, well actually, seriously, like in order to write a Taylor series, what do you have to write first? Okay, and
you have
then
to
the
write the
Taylor
polynomial.
polynomial, right? So please know that in order to write a Taylor series tonight, when it says write the series, always start by writing the polynomial first, then create the series, okay? Polynomial first, then create the series. And can you take a known series and create a new series by modifying the input or the function in the series algebraically?
Yes, I can.
Yes, you can. Good. Okay. So let me turn off the video and then we're going to work on our quiz.
Oh.
Bye.